So ladies and gentlemen, here we are given a problem on balancing rotating masses. Now, four bodies in a plane are rigidly attached to a shaft, rotating at 500 r.p.m. by means of levers. Their masses, radii of rotation, and relative angular positions are given below. We are told that we have a body A of 2 kilogram, radius at 1.2 meters from the axis of rotation and at an angle of 0 degrees. B, C, all with their respective angles. So we are told that we need to find the magnitude and position of the balancing mass if it is placed at 0.8 meters from the axis of rotation in the same plane. So what we have to understand here in such problems, it is okay to sketch. You can have a reference point. So you have, for example, this one at 0 degrees, you can make it to be your reference point. That is your A. Then the next one, which is B, is at 60 degrees. The one at 60 degrees with the horizontal is B. This is B. And remember, the 60 degrees, if it is positive, then it is in the side of anti-clockwise direction. Then uh, the C, body C, at a distance 0.4, this is C, is at an angle of 120 degrees from the reference point. So 120 degrees, this is 60 degrees, this is the reference point. Then what about the last one is body B, I mean body D is at an angle of 135 degrees. So 135 degrees is at a distance of 0.2. Let me just assume it is there. So this is D. And from here to there should be 130 degrees. So we are told to find the magnitude and direction of the balancing mass if it is placed at 0.8 meters from the axis of rotation in the same plane. Now, we already know that that same mass is going to be produced by the resultant force. So we are going to first look for the sum of vertical forces. So sum of vertical forces acting on this shaft. We are assuming that this is the shaft and maybe the axis of rotation is somewhere there. So these are masses that are acting on this shaft that is rotating. Some of the vertical forces must always equal to, we are going to have, maybe this is M1, this is M2, this is M3, this is M4. And the mass that is needed, we are going to let the mass be, for example, M. That is the mass that we need, okay? The mass for balancing this system. Now, let's do the math very fast. So now, M1 is already horizontal. So, if we are looking for the vertical component of this force, it is M1 omega squared R1 sine of 0 degrees, because the angle with which it makes with the vertical is 0. Then plus M2 omega squared, these are forces that are centrifugal set on these masses. So these are centrifugal forces. So this is R2, and we are going to take sine of the angle with which it makes with the horizontal, and that is 60. Then we add M3 omega squared R3 of sine 120 degrees plus M4 omega squared R4 sine 135 degrees. But now, since we know that the vertical component is also going to be having this omega squared, we are going to leave it out so that at the end of the day, whatever we have does not have omega, because even omega has not been provided to us, but we can work without it, because this other force, the sum of vertical forces, is going to be having an omega component, so which can cancel out and will remain with the r and m and the sine of the angle. So this is going to be sum of forces that are vertical is equal to, this is 0 because sine of 0 is 0, then plus m2. Those forces, those masses are given up here. So body B is 4 times the distance, which is 0 0.8, 0 0.8, 0 0.8 times sine of what? Sine of 60, which is root 3 out of 2. I told you these ratios, so you should be able to see them and know. Then M3 is 6 kilograms at the distance of 0 0.4. So 6 times 0 0.4 times sine of 120. Sine of 120. So 120, sine 120 is also root 3 out of 2. Then plus M4. M4 is 8 times 0 0.2 times sine of 135. Sine 135. So sine 135 is root 2 out of 2, because it is the same as sine of 45 degrees. Sum of forces in the vertical direction is going to be, so there I have 4 times 0 0.4 times root 3, then plus I have 3 times 0.4 times root 3, then plus 0.1 times 8 times root 2. So I have 5.981, and this is, that is the force. Since I have radius and the mass, I can call it kilogram meters, because the units I have here is mass times r, whereby mass is in kilograms, radius is in meters. Let's look at sum of forces in the horizontal direction. So I'll just revert the sign to cos. So I'll have m1, which will be, already know, m1 is 2. So this will be 2 times the distance. The distance is 1.2. So 1.2 times cos of 0, because this makes an angle 0 with horizontal. So since I'm taking the horizontal component, then I'm talking about a cos. A sine takes up a vertical component. So cos 0 plus 4 times 0 0.8 times cos of 60 plus m3. M3, we said it is 6 times 0 0.4, which is the radius, times cos of 120. Cos of 120 is negative a half. It's the same as cos 60. Then plus m4 times distance, which is r4, 0 0.2, times cosine of 135, which is also the same as negative root 2 out of 2. Is the same as negative cosine of 45. So this is going to give me 2 times 1.2, cos 0 is 1, so plus 4 times 0.8 here, times a half, because cos 60 is a half. So 4 times zero point 0.8 cos 60 plus 6 times zero point 0.4 times negative zero point 0.5, then plus 8 times zero point 0.2, then times cosine of 135. So what I'm getting here is 1.67 kilogram meters, because those are the units I'm dealing with here. So what is the resultant? So resultant will be sum of horizontal squared plus sum of vertical squared, everything under root. So R will be 1.67 squared plus 5.981 squared, everything under root. So 1.67 squared plus 5.981 squared, I take root. So my answer is equal to 6.21. So meaning that the resultant or the balancing force must equal to R. So if we said if the balancing mass is equal to M, then that means M times its radius, it should equal to R. It should equal to 6.21. But the radius is given as 0.8 according to the question. So meaning I'm going to have M times 0.8 should equal to 6.21. So meaning M is equal to 6.21 divided by 0.8, and this is equal to 7.76 kilograms. So this is the mass that should be introduced in, so that we are able to counterbalance the system and avoid the resultant. But let us look at the direction of the resultant R with the horizontal. Remember, all the vertical and horizontal components are positive. So I'm expecting my resultant in the first quadrant. So let's look for maybe tan alpha will equal to sum of forces in the vertical direction divided by sum of forces in the horizontal direction. So the vertical one was 5.981, the horizontal one was 1.67. 5.981 divided by 1.67, I take tan arc over the answer, and I have 74.4 degrees. If that is the angle with which the horizontal makes with the vertical, I mean with the horizontal, this is 5.981, this is 1.67, and this is the resultant R. If this is 74.4 degrees, and the force to counteract the system must act opposite directly along the arc line of action of this R, but opposite. So what is going to be the angle with which it is going to make with the horizontal? Obviously, from here to here is 180 degrees. This is 180 degrees. So the total angle, let me call this R prime. So angle with which R prime acts with the horizontal will equal to 180 degrees plus 74.4 degrees. So plus 180, and this is becoming 254.4 degrees. Therefore, the mass, the counterbalancing mass, must be placed at an angle of 254.4 degrees, okay, with the horizontal. and at a radius given of 0.8 meters from the axis of rotation of the shaft. So this is how we do these things of balancing.